Hey there. So let's see. Today we're going to finish off the complexity lecture. None of the exam questions come from this component of the lecture. And the sound quality is going to be a little bit iffy because there's a hurricane going on outside. The rain has already started. You can see it out there. It's raining. But the wind won't pick up until later on this afternoon and evening. I'm trying to wrangle my friends over to loiter around and play video games during the hurricane itself rather than perseverate with the dog while it shakes uncontrollably. Anyway, so the lecture today should be short, and I'll have my question and answer session with you guys in a small number of hours when the wind might actually be pretty substantial. It will, I'm only going to be on the southern component of the storm, but we'll see. Anyway, I'm getting enough rain that it should flood the neighborhood and blah, blah, blah. And yep, should be neat. Anyway, so self-organization. Self-organization is that a general property that once there are a small number of rules, simple rules that the constituents, the pieces of a complex system follow, even if they're homogeneous rules, it can produce patterns at the level of the system that will make it look like there's some sort of central command, like there's some sort of higher order process that's making sure all of these, this organization emerges. So self-organization is also sometimes referred to as spontaneous order, and that's that, like the individual members of a complex system, like individual members of this murmurating flock of starlings on the right-hand side here, are each following just a small number of really simple rules of what to do and how to move relative to your neighbors. But if you look at these swirls and movements of these flocks, it looks like it's like one giant organism sliding around, and they must be communicating with each other in some way, some sophisticated notion, or there must be some leader calling out commands. But the reality is that those birds in that flock are only following a small number of really simple rules, and that creates all of the incredible structures and organic movements that murmurating flocks or schools of fish create. So self-organization is oftentimes typified in really non-humanesque sorts of organisms. So like people oftentimes think about like how do ant colonies know how to assign workers to various kinds of tasks? When the colony is being attacked, how does the colony know that it's being attacked? And how does it know that it needs to shunt workers into colony defense? Or when there's food outside that needs to be gathered, like there's a pulse of food, how does the colony know to send out more and more workers? Well, one of the hypotheses is that like there are little leader ants inside the society, like this, queen from A Bug's Life over here that's got a pet aphid that has some sort of sugar excretum that it excreta that it provides her with, maybe, and that like they're like little rulers or something, and there must be like little administrators in these ant societies, but that's not true at all. Like no one tells an ant to go do this or that. There is no command structure. There are no administrators. So, the average ant, as I've referenced before, and I'll probably reference again when I talk about ants as a taxonomic group later on, probably starting next week, the average ant has a memory of about 10 seconds. It knows-ish we don't really know what an ant knows, but we know-ish that it probably knows where it's been in the last 10 seconds, what sorts of things it's come into contact with the last 10 seconds, and that's really about it. And so without a manager and with an average memory of about 10 seconds, how do you get all these workers to create these complex dynamics, like how to adaptively shunt individuals between the relevant tasks that a colony needs in order to survive in a dynamic environment where the challenges are varying all the time, right? So this example that we'll talk about with a little bit of depth here will be how colonies respond to food pulses when they know to send out more workers because there's lots of food out today, and how they know how to send very few workers out in days where there's just not that much food, right? And I'll let you know, it probably has something to do with feedbacks, and it probably has something to do with self-organization. So colonies on the whole adaptively allocate workers, but they don't have a queen or slave drivers or whatever, or admins or executives to tell them what to do. So it would be like the analog of what these ants have to basically do is like if there was an orchestra playing a piece together, but there was no conductor at the front of the room telling who commanding synchrony of the orchestra, and without any sheet music either, right? So there's no sheet music. They're all just, this whole orchestra is basically challenged to play a piece with no sheet music, no director, and just paying attention to the immediate musicians around them. That's how challenging this task is. But yeah, these ants are capable of doing something very impressive. Mind you, it's repetitive. They're not playing new pieces all the time. It's highly repetitive and predictable. And they, to some degree, the same challenge all the time. But they follow a small number of rules that allow the whole colony to dynamically determine how to allocate its workers. So the ants have a second, we're talking about harvester ants in this instance. The ants only have a memory of about 10 seconds. So what the hell do they know, right? But the answer is they know basically whether or not they've come into contact with other ants in the last 10 seconds. And when they do, when two ants come into contact with each other, they antennate each other. They basically palpate each other's heads with their antennae, and that allows them to taste the particular hydrocarbons, which is like a fatty grease that covers the exterior of the ants. On the one hand, it prevents the ants from being desiccated, right? It's like a little white waxy covering on the ants to prevent them from drying out, which is a problem when you're teeny tiny and you have a surface area to volume ratio that's high and you're outside in an arid environment like a lot of seed harvester ants are. But that grease also, whenever those ants are wandering around outside or inside or come into contact with an enemy or with food or whatever, that grease picks up some of those chemicals so that when one ant touches another, it knows that it came into contact with another worker, and it has some information about what that worker has been doing. Whether or not that worker was out foraging, whether or not that worker was out foraging and was successful, whether or not that worker was out foraging and unsuccessful, whether or not that worker has been in the queen's chamber feeding brood, or whether or not that worker has been outside the colony at all recently. So this grease, just like by happenstance, by wandering around in the environment, picks up tiny little chemical molecules that then are used as a cue by other workers when they're coming into contact with that focal worker, where that focal worker has been, whether they've been successful, and what they've been doing. Right. So basically with this adaptive allocation of ant workers, there's a bunch of ants that just sit inside the vestibule. The first, man, the wind is really picking up. God, I mean, I don't know if you can see it, but there it is, whipping around. Anyway, so it's not me. It's not the hurricane that's the focus of today's lecture, but it's a mild hurricane. I'll be fine, but I do sleep right next to a giant window, so I'm fine. Anyway, so the workers can taste, so a bunch of ants are waiting in the vestibule, the main entrance to the colony, right? And when each morning, the colony sends out a small number of scouts ants that just go out every morning. When those scouts go out, they'll wander around in the immediate vicinity of the colony on common foraging trails, and they'll see if they find food. If they come back with no food, the ants waiting in the vestibule antennate those returning scouts, and they basically can tell whether or not that scout brought that food, or whether it interacted with food while it was out there. If it did, then that cues other ants to go out and start foraging. When they come back, if they come back with food, that cues yet more ants to be more likely to go out and forage. And this creates a positive feedback loop. So when there's lots of returning ants with food, the colony sends out more and more ants. When those workers start coming back without food, those ants that are thinking about joining or going back out for another foraging trip stop going out. So the individual ants inside the colony don't know how much food there is outside at any moment in time, but they can figure out the gist of how much food is outside and how many workers need to go out by basically just determining the rate that ants are coming back with food versus the rate with which ants are coming back without food over the last 10 seconds. And some workers tons of workers are just waiting there deciding whether or not to go out. Yes, individual workers vary with how easily they'll go out to forage. Some workers are more likely than others to go out and forage. So there's some workers that basically have like a little instinct that tells them okay, if you interact with 4 returning workers with food over the last 10 seconds, you go out. Other workers have a different rate. If you interact with 2 returning workers with food coming from the outside over the last 10 seconds, you go out. But in the end, that returning food rate will breach some number of thresholds of the workers inside of that colony and trigger them to go out. When they start going out food outside and they don't come with that, don't have any food that they obtain, and they come back without food, that will tell those returning ants, the ants waiting in the vestibule, which is protected from the sun and from desiccation, that the food is depleted and that they don't need to go out. So an individual colony could send out hundreds or thousands of workers on days where there's lots of food, or 10 workers, which are merely scouts, on days where there's very little food. And this protects the colony from losing too many workers for no reason, to like desiccation or to predators on days when there's no food to go obtain. So despite the fact that each worker only has about a 10-second memory, it can use the rates of interactions with other workers that are performing various kinds of tasks over the last 10 seconds to determine what it should be doing. So if I'm interacting with lots of successful foragers, I should go out and forage because there's still food out there. If I'm interacting with very few returning successful foragers, then that means that on average, I'm not finding that much food, and it's better for me to stay here because it's better that I stay here and not die than I go out and possibly risk perishing from desiccating in the desert air when there's no food to be obtained. Another example is like, okay, fish schools. Fish schools produce these beautiful like swirls and swarms and dynamic movements in response to predators. How do they do that? How do they know where all the other fish are? And how do they know that they're making these beautiful images? The answer is these fish have no idea what kind of picture they're making for your desktop. They don't know whether or not they're making some beautiful image. They don't give a crap. And the predators don't really attend to that geometry either, right? It's visually appealing to us because it's orderly. Humans find order immensely appealing. Animals, they don't really find order appealing unless they've been selected via natural selection or other evolutionary processes to find order appealing. Order just emerges, these beautiful swirls and murmurations and things of schools or flocks of birds, or even trails of ants emerge because these ants, these fish, these individual birds are following just a small number of rules. When you sum all those rules together across all these individuals, it creates a collective dynamic that is probably unperceivable to the constituents of the groups. Like, they don't know what they're doing. They don't know that they're making something pretty. Anyway, so these fish here basically just have 3 rules. So fish have eyes on the side of their head, but they're oriented slightly towards the anterior. So from about this alpha direction back, the fish can't really see behind it. It can only really see in front of it. If the fish is far away, so beyond this sphere of distance, this circle of distance, if it's far away from conspecifics, the fish swims as quickly as possible towards other members of its group. Once it's within this intermediate range, the only rule it follows is align with your neighbors. The average neighbor, wherever they're going, you make that same angle. Oh, they've gone that way. The average angle's this way. I'm going that direction. So there's an orientation, intermediate distance. And then if you, by happenstance, get very, very close to one of your neighbors, move back slightly or slow down relative to the rest of the group to move back from that individual. Following those 3 basic rules. Move towards conspecifics, the largest group of them, if you are far away. Then secondarily, at an intermediate distance, align your orientation of your body with the average individual around you. And then lastly, if you're too close to somebody, back up a little bit. That's all that needs to happen to create these swirls and these beautiful geometries at the level of the group. Isn't that neat? This apparent order, this apparent beauty that, you know, artists create in human society is inadvertent art created by animal societies because they're just following a small number of rules, and a small number of rules can create incredibly complex outcomes. Mathematically, this is pretty simple to model. and then the output of the group, it produces tons of different geometries that they can adopt and patterns that appear like they are doing something different in each kind of swirl that they could create, but they're not really doing anything different. All those fish are basically just following these same 3 basic rules. That's it, and that's all it takes. Wow. All right, hierarchical organization. I kind of touched on this already, but we'll go over it again now. No joke, complex systems have parts that are following rules and aggregates that are creating patterns. But complexity theory, what is a system, depends on your focal level of study, right? I mentioned in connectedness that you can talk about a brain being a complex system, or a blood cell being a complex system, or an amoeba being a complex system, or you could talk about planet Earth in its entirety being a complex system. It could be economics, it can be social groups, it can be cities, it can be organisms. All of them use the same kinds of math and follow the same kinds of general principles. And shockingly, these sorts of topics innervate all of these fields. Scientists and non-scientists studying all of these properties in different fields have lots of crosstalk in complexity theory. Hierarchical organization. Human societies, look at a business. Like, there's just tons and tons and tons of nested structure inside of a business, right? And so to figure out how a business operates in the aggregate level, you have to know to some degree how it's organized in its subunits, and the subunits of those subunits, and the subunits of the subunits of the subunits. So there are, there are team leaders, and then there are managers, and then there are various sectors inside of a company, and then there's a CEO, and then there's staff. I mean, in the case of a human social structures, we oftentimes have central management, CEOs, but CEOs aren't dictating every interpersonal interaction inside of each team, inside of a corporation, right? That's not happening. So corporations are to some degree influenced by top-down control, central management that's telling individuals what to do, leaders and followers in a power dynamic sort of situation. But much of what happens is, again, just spontaneous, right? Office politics just emerge spontaneously in every single possible team. That is from a small number of self-organizational processes again and again and again. Nobody tells them to exhibit that high level of parallelism in the social dynamics across companies of various kinds across the whole world. That just happens from simple self-organizational processes. Biology is hierarchical too, right? Yes, you have atoms, you have molecules, you have cells, you have organelles, you have cells, you have tissues, you have organs, you have systems, organ systems, you have organisms, you have populations, all the way up to biomes and the biosphere of planet Earth. Figuring out what's happening at any one of these levels is going to require you tunneling up and down to different tiers of organization and applying principles in complexity theory. The states of one system, the outputs of one tier of organization, influence the parameters at another tier of organization. And so that means that those jiggling around of a system within a basin of attraction is oftentimes determined based on feedback loops and things, interactions, connectedness between subsystems or systems occurring at higher tiers of organization. That's it. Hierarchical organization plus connectedness yields a general pattern that describes all of life. I mean, to some degree, it's obvious. Hierarchical organization. Oh, these are Saiga. I don't actually know why I showed you Saiga. Saiga are super neat. I think they mostly produce twins. They look like a leftover from the Ice Age, and they basically are. They're critically endangered. They're from steppe habitat in Eastern Europe and Western Asia. And they have these kind of cool noses, which again makes them look like they should be extinct. And they're famous for having botflies that fly up their noses. You know, botflies are tiny little flies that lay a larva on the inside of epithelial tissue that then pops out later on in life. Anyway, their noses are often infested with botflies. What do you know? Saiga. They're pretty cool. Anyway, there they are, S-A-I-G-A. I don't know why I have them here. I think I just liked them because they matched this, this tan. I was like, I wonder if these students have seen Saiga. Here you go, Saiga. Anyway, so understanding any complex system requires tunneling up and down between tiers of organization. And that means that in order for us to understand any tier of organization, we have to have crosstalk between different disciplinary boundaries. That's almost certainly an option on one of your exam questions, but it's something I've said before. States and parameters. The states of one system feed back into the parameters of other systems. Parameters are oftentimes shared by multiple systems, right? Lots of different animal populations are all influenced by the same climatic patterns, right? And climatic patterns can be a parameter on the x-axis of many different kinds of outcomes that people could look at in an animal population. Its population size, its growth rate, its levels of infection of some sort of disease that you're interested in, whatever your response variable is. So many systems share parameters because the same parameters are influencing all of them simultaneously. Many systems, via connectedness, have their states influencing the parameters of other systems in a highly interconnected way. All right, determinism and chaos. I talked about this once already, but I'll just briefly go over it again. Just because something is very difficult to predict does not mean it's not deterministic. And so chaos, unpredictability, can still come out of a system that has a small number of rules it's following. And so the classic example of this is the Lorentz attractor state. Look at this swirly whirl thing over here. What is this swirly whirling thing? This equation basically plots the state of a system of convection. So basically it's just convection, molecules, a physical system. There is no living thing here. And they describe the movement of molecules when being heated, right? And the molecule will slide around in space in a highly deterministic way, following just three very simple differential equations that determine the path of that molecule, right? And the state of that system, its behavior, changes in a way that's very difficult to predict. So it's swirling around in a way that seems like it's making sense, it's crescendoing out, and then or moving in, and then all of a sudden when it gets further and further in, there gets to a key state where it flips to a totally different set of orbit. The system starts to follow a different kind of dynamic entirely. If you were trying to predict where this molecule is going to be in the future, the behavior of this molecule as it's swirling around in space, you would have a very difficult time because scientists don't know the differential equations, the central mathematical properties, the key levers of life and physical systems that are telling it what to do. We're just trying to figure out what those rules could be using experiments and natural observations. So given the fact that even this very simple system that has just three very simple differential equations to describe the movement of that molecule, look at how difficult it would be to predict what it's going to do next. It follows one pattern for a little while, and then all of a sudden it flips entirely and it starts spinning outward over here. Then it flips back over in sort of a butterfly shape over and over and over, and it follows that for a little while until it begins to swirl around some interior state, and then flips again. And you can just watch a computer solve the path of that molecule in real time. It'll create this beautiful set of swirls that look like a butterfly, right? The butterfly effect. Imagine one of the issues with this is that if the molecule starts off in just the slightest little difference in space, right? The tiniest little difference, it could take a totally different path. So if you're just, microns off, it would follow a different path. It would, instead of swirling out, it would swirl inward. Or instead of continuing to swirl for a long period of time, it will flip to another kind of geometry, begin swirling in a different pattern, right? So, okay, so very small differences in the starting state of any system can cause it to take a very different path. All right, well, that's simple, right? So we just figure out what the relationship is between the starting state of a system, and we'll be able to figure out what it will do, right? Problem. Almost every complex system, the way we measure its starting state is imperfect. Right? Even among clones, we're like, okay, we have the same starting conditions. They're all in identical sensory deprivation chambers, but in every way that we can measure, those starting conditions, those clones are identical. But they're not. There are infinitesimally small differences between those replicates, despite the fact that they were on clones, reared in identical sensory deprivation environments. There were differences in their physiological states, in their behavioral states, even in their genetics after a little while, that we can't measure. They're so small that we can't reliably measure them, which means that we won't be able to set up parallel systems to study that outcome. And we'll see our little organisms that we're studying in sensory deprivation chambers that are all clones take on wildly different trajectories in life. In many instances, twins are oftentimes like each other, but when we talk about that a lot, is like the genetics underlying human behavior and development, right? Twins oftentimes resemble each other, even when they're reared in completely different settings. But by parallel logic, even when twins are reared under very, very similar settings, they can be wildly different behaviorally. Just like clones, clonal fish, we'll say, reared in sensory deprivation chambers can develop entirely different personalities, entirely different social tendencies. And that's because there's always going to be infinitesimally small differences in the state of anything you want to study. And the problem with that is that if there are a small number of deterministic rules that can create very complex outcomes, then we're going to have a very hard time predicting what's going to happen to those individuals, because they were unlike each other in a small and immeasurable way, and that can create wildly different developmental trajectories, or in this case of this convection of an inorganic molecule, just its path and where it goes around, right? So we can't even measure, the position of a molecule to a high enough level of precision to be able to predict where it would move in this path. We're always going to be indistinguishably close to two different paths or many different paths, and so it's going to look like total randomness to the human eye or to a statistical model or to a computer, and that's just the facts. It doesn't mean that life is totally random. Very few things in life are actually random. There are deterministic processes determining most of patterns of life in physical systems, but because we're just not that good at measuring them, and there's so much state and environmental dependence, we cannot be shocked when we're bad at estimating what's going to happen in the future. I mean, if we're following this molecule for a little while, we'll be able to say, okay, for the next time step, we kind of know where it's going to be. In the next time step, we're kind of know where it's going to be. In the next time step, we're kind of know where it's going to be. But as we look further and further into the future, it gets more and more difficult to predict where that molecule is going to be, where that personality type is going to be, what that social group is going to be doing, even though it's following the same deterministic sorts of processes. So predictability decays the longer you into the horizon you're trying to predict the behavior of any complex system, its state. And immeasurably small starting differences can cause apparent randomness, but it's not actually random at all. There's a set, it's the same rules that it's following. It's just you can't measure well enough to know where exactly it is in state to know where it's going to go next. So it's popular among some people to say, like, a butterfly flaps its wings in one system could cause a hurricane in another system, in a coupled system, by connectedness. And that basically comes from, one, when you plot things like the Lorentz or attractor states, it makes beautiful butterflies, right? Like little, like that looks like a butterfly, hooray. But then it also sort of brings home the message that, like, immeasurably small impacts from within your focal system or a connected system can cause your focal system, climate, tropical cyclones like the one outside right now, to take different trajectories, to have different outcomes. And so on the one hand, you could say, oh my God, how are we ever going to predict anything? But the other hand, it's basically just go easy on yourselves and go easy on science in general when it's just trying to make the best predictive models of a very complex situation. And very small impacts that seem like they should be entirely irrelevant and would be almost impossible to detect based on our current abilities can cause wildly different gross outcomes in the state of the system and where it moves in the future. So that's the butterfly effect. So with that, I will leave you guys be. I think this was a short lecture. I hope it was a short lecture. I hope it recorded effectively. And I'll see you guys in just like an hour, right? Yeah, I think so. Like maybe 2.5 hours. It's 2 p.m. Yeah, 2.5 hours. All right, see you later. Take care.